A key but often underappreciated factor in aging is the gradual loss of precise epigenetic control, known as epigenetic drift. This process refers to the progressive, seemingly chaotic changes in DNA methylation patterns and histone modifications that disrupt the finely tuned orchestration of gene expression, leading to inappropriate activation or silencing of genes. Epigenetic drift has been closely linked to many hallmarks of aging, including increased inflammation, impaired tissue regeneration, and metabolic dysfunction. Yet what is frequently overlooked is that the machinery of epigenetic maintenance depends fundamentally on an adequate supply of dietary methyl donors, without which these regulatory processes cannot function optimally. Acetylmethionine, same. The universal methyl group donor for DNA and histone methylation, is synthesized in the body from methionine, an essential amino acid, along with cofactors including folate, vitamin B9, vitamin B12, and choline. These nutrients enable the 1-carbon metabolism pathways that supply methyl groups required for proper epigenetic programming. When diets are low in these critical nutrients, the production of same declines, resulting in insufficient methylation capacity. This deficit leads directly to erratic methylation patterns across the genome, causing unbalanced gene expression profiles that closely resemble the epigenetic signatures observed in aging tissues. For example, hypermethylation of promoters of genes involved in DNA repair can silence these protective pathways, accelerating genomic instability, while hypomethylation of pro-inflammatory genes can lead to chronic, systemic inflammation, both of which are strongly associated with biological aging. Importantly, these maladaptive epigenetic patterns are not immutable. Multiple studies show that restoring adequate intake of methyl donors through diets rich in leafy greens, eggs, organ meats, legumes, and fortified grains can favorably influence DNA methylation patterns, often reversing or slowing the epigenetic drift tied to aging phenotypes. Furthermore, observational and interventional research demonstrates that individuals with sufficient folate and B12 levels display DNA methylation profiles indicative of slower biological aging, with reduced risk of age-related conditions such as cardiovascular disease, neurodegeneration, and immune dysfunction. Conversely, people with long-term deficiencies in these nutrients tend to exhibit accelerated epigenetic clocks, which measure biological rather than chronological age, correlating with poorer health outcomes. This compelling evidence reframes age-related epigenetic drift not as an irreversible or mysterious degeneration, but as a predictable consequence of chronic dietary insufficiency in methyl donor nutrients. By ensuring adequate intake of these nutrients throughout life, it becomes possible to maintain more youthful patterns of gene expression, preserving cellular function and tissue integrity far beyond what is typically observed in Western dietary patterns lacking these key compounds. Ultimately, recognizing that the destabilization of our epigenome with age stems largely from preventable nutritional shortfalls adds yet another layer of support for viewing aging as a form of subtle malnutrition rather than an intrinsic disease. This perspective provides a clear, actionable path to influencing the rate of biological aging by emphasizing lifelong nutritional adequacy, shifting the conversation away from disease management and toward proactive maintenance of genomic and cellular health.